Why is an op-amp rarely used as a differentiator? We are going to look at that in this video. Let's get started. I'm going to first explain you how the differentiator works and how the integrator works, and then explain you why we are rarely using an op-amp as a differentiator. So if you just want the answer, you can use the timeline and the chapters that is added to scroll to the section that you want. Let's first learn the integrator. In the integrator, in the input we have a resistance, and in the feedback path we have a capacitance, and let us label this to be CF. And we are supplying this with plus VCC and minus VEE. Okay, so let us straight away apply KCL at this node, assuming this to be an ideal operation amplifier. I am not going to go into the basics because we have got a lot of videos in this topic, and by this time you should be able to apply Kirchhoff's current law at this node. Okay, so the current that is entering here is the same as the current that is entering through this capacitor, right? So by the Kirchhoff's current law, the current that is entering through R1 is same as the current that is entering into this capacitor. What is this current? It is the difference in the voltage between these two nodes divided by this resistor, correct? So the current through R1 is Vin minus 0 divided by R1, which is equal to C into the difference between the differential of the voltage between the ends, which is 0 minus V out. So this implies that minus V in by R1 is equal to C into the differential of output voltage. So to find out the output voltage, we have to integrate both sides. So let's integrate both sides now, and we will be getting minus 1 by R1 into the integral of V in is equal to C, or this is actually CF. I have just written C here. So this is CF into the output voltage. Which implies that the value of the output voltage is equal to minus 1 by R1 into CF to the integral of the input voltage. The output voltage is an integral of the input voltage, okay, and the gain factor is minus 1 by R1 into CF. This is the gain, which is called as the integral gain, and this is the integral of the input. Okay, so the output voltage is an integral of the input voltage. Now, when the frequency of the input signal increases, what will happen to the capacitive reactance? This will have an effect on the output voltage because the capacitance is susceptible to frequency. What is the capacitive reactance? 1 by omega C, right? So when this frequency increases and increases and increases, and let us say it is even approaching infinity, what happens? The reactance is 0, and thus the gain reduces, but there is no distortion in the output that is observed at very high frequencies. So this integrator, it's operable only at a band of frequencies. It is susceptible only up to a minimum level of frequency. When the value of the frequency approaches infinity, what happens to the capacitive reactance? The capacitive reactance approaches 0 and this condition. So this frequency response tells you one thing. You can use this only after a certain minimum level of frequency, but not in the lower range of frequencies. Okay, because in the lower range of frequencies, what will happen? The gain will be stable, that's not a problem. But what is the actual problem here? When the frequency is close to 0, the capacitance the capacitive reactance will approach infinity, and thus there will be more distortion in the output. So to minimize this, we connect a compensative resistor RF in parallel to CF to eliminate this distortion, because this excess in output will have a place to go to, and thus the feedback path will be smooth. So therefore, at a minimum frequency, let us call it as F1, which is equal to 1 by 2 pi into R1 into C1. So we are going to use the circuit as an integrator beyond this frequency. Of course, this goes up to unity gain bandwidth, which is equal to the frequency at which the gain becomes 1. Let us draw the frequency response to have a clarity. So this is the frequency response of a general op-amp, right? And this is the open loop gain. And if you observe, after a certain level of frequency, which is called as F1, and this extends up to the unity gain frequency, where this is the frequency at which the gain becomes 1. Okay, so in this range, the op-amp acts as an integrator. How to find out this frequency? This is 1 divided by 2 pi into R1 into C1. And this is the minimum frequency in which you can operate this op-amp as an integrator. This is integrator, and now let us see the circuit of differentiator. In a differentiator, we have a capacitive at the input, we have a capacitance at the input, and we have a resistance connected in the feedback part. This is the main difference between a differentiator and the integrator. Let's call this resistance to be RF. If we apply Kirchhoff's current law in this node, we will be getting the current through the capacitance C1 is same as the current through the resistance R1 by KCL. So the current through the capacitance will be C1 times the differential of the voltage between these two ends, which is Vin minus 0, which is Vn. Okay, because this is 0 volt, this is Vn, the difference is Vn minus 0, Vn. Okay, so the current through RF, okay, this is not R1, this is RF. The current through RF will be 0 minus V out divided by RF. So what is V out? So this implies that the value of V out is equal to C1 into RF times the differential of the input voltage, and that is why this is called as a differentiator. So let's understand the effect of frequency. Okay, this is the gain, differentiator gain, and this is the differential of the input signal. Let's see how the gain varies with respect to frequency. So the gain in this case is C1 into RF. So at a high frequency, what happens? The value of XC1 is equal to 1 by C omega. So when frequency is increasing and it approaches infinity, this becomes 0. So what happens? The gain diminishes at higher frequencies, and at lower frequencies this is possible. Okay, so when omega is low, what happens? The value of XC1 approaches infinity, and thus there will be distortion. Normally we operate the op-amp circuitry within the stable range of the op-amp, because at higher frequencies, you have seen the graph, it slopes down, and only at a frequency up to the cutoff frequency, the gain is stable. So we always operate the op-amp in the stable range, which ranges from 0 up to the cutoff frequency of the op-amp. In this range, what happens to a differentiator? There will be distortion in the output, because in lower range of frequencies, the capacitive reactance approaches infinity, and thus what happens? the noise signal will be so high that the actual signal of the op-amp is getting overridden. So there will be distortion in the differentiator's output. So normally we don't use op-amp for using it as a differentiator circuit. This is the reason. We will also solve one problem in this concept. In the figure, the operational amplifiers are ideal and their output can swing between -15 and +15 volts. Sketch on the same diagram the waveform of voltages V1 and V2 as a function of time. You must give the values of important parameters of the sketch. In this question, we have an information that both these op-amps operate within the range +15 and -15 volt. So this means that the operating power supplies are plus and -15. This one is a voltage follower and this is a integrator. Okay, so what does a voltage follower do? It just repeats the input that is given to it, which is plus and -15 volt. So what will be the value of V1? The V1 will be +15 volt at one instant, and then it will reduce to -15 volt. Okay, so this is actually a positive feedback case. So let's have V1 aside and let's draw the circuit response of the integrator. The response of V1 is applied over here to this integrator. Now let's presume the value of this voltage to be V and see how much is the value of the current that's through this circuit by applying Kirchhoff's current law. Okay, this V is actually 0 volt because of virtual ground concept. This V is 0 volt, and let's do the equations. V divided by 1 kilo ohm plus V minus V1 divided by 3 kilo ohm plus V minus V2 divided by 1 kilo ohm is 0. So this implies that by virtual ground concept, this is 0 volt, and hence the voltage at this end is also 0 volt, so which implies that V is also 0. So this implies that minus V1 by 3 is equal to V2 by 1. So what is V1? V1 will be minus 3 times V2. We have sketched the value of V1 in this curve, and let's formulate the value of V2 by this case. When V1 is 15, what will be V2? V2 will be 15 divided by minus 3, which is equal to minus 5. So when V1 is plus 15, V2 will be minus 5, which will be approximately here. And same, when V2 is equal to when V1 is minus 15, the value of V2 will be plus 5. Okay, and the same thing repeats. Okay, let me explain you. When V1 is equal to plus 15, the value of V2 will be minus 5, and when V1 is equal to minus 15, what is the value of V2? It will be plus 5 by this equation. Okay, so we have sketched that and we have drawn the waveforms of V1 and V2. This is the integrator. Okay, thanks for watching. We have seen a whole lot of concepts in OPAMP, which is available in this playlist. If you have any doubts, you can just type that down in the comment section or email to learningtoengineer@gmail.com. Thank you.